Right, we now move to acceleration during launch. Up until now, we've been talking about projectile motion, which we have by throwing or projecting an object at an angle to the horizon. But in acceleration of a rocket, because a rocket is self-powered, we have an internal source of energy pushing the rocket into space. It'll take a few moments just to have a look at a shuttle launch. Okay, so we just had a look at a shuttle launch. Now shuttles these days are being no longer used, but it's a good example of how we get into space. The shuttle has a large booster rocket, as we saw there, and the actual launch vehicle lies on top of it like that. And there's the cockpit up here, there's that, and there's the wings. And what will happen is once the rockets here are turned on, we get the gases from the rocket, the actual engine, being spewed out the back. There are two smaller booster rockets that are on either side of this rocket, and these ones are reusable, and they are stabilising, and they do other type of rockets. They actually are used for manoeuvring within the launch. But the majority of the fuel is hydrogen and oxygen, and when they combine, you simply get water going out the back. But the water is in the form of steam. It's a hot gas, very, very hot gas, and the expansion of this gas causes the shuttle to move forward. And we call this forward motion, or the forward force, thrust. The booster rockets uses an aluminium type fuel, which is slightly different than the hydrogen oxygen fuel. Okay, so looking at our rocket here, let's have a look at the actual forces. The first force that we just discovered on the rocket is a forward thrusting force. And so here, we're going to give it the letter T. The other force that pulls the rocket down towards the centre of the Earth is the force of gravity, and its technical term is the weight force. So this is the force of gravity here. And we know that the force of gravity is given by mass times the gravitational acceleration, which is 9.8. So just to work out the total overall forces, this is the net force on a rocket. The net forces on a rocket would be the vertical thrust force, this is the T here, minus the weight force, mg. Now we'd only get motion upward if T is greater than mg. If it equals mg, then we are just on that point of forward motion. Okay? So what will happen is at the moment of blast off or lift off, we will be starting to make this thrust coming out the back increase until we just get a point where it starts to move, and then up it would start to accelerate. Now the net force according to Newton's second law, is because F equals ma, this becomes ma equals this expression. So to find the acceleration, we simply need to divide by m. And so we are left with this equation here, which says the acceleration of a rocket is equal to the thrust minus mg divided by m. Now, to keep in mind that an astronaut which is in the top of our rocket, and I've drawn the astronaut there as lying horizontally, and there are reasons for that, which I'll get into later, the astronaut will accelerate at the same acceleration rate as the actual rocket. So all objects within the rocket will accelerate at this acceleration rate here. So that's to keep in mind, because it's going to be quite important as we have a look at the different forces on our astronauts. Now, when a person sits on a chair, so here's a person, there's our chair. There's our chair just here. It's not drawing, oh, it's white. It's not. There's our person sitting, it's the back side. The reason why you feel the chair is the chair pushes up just as much as you push down. They're equal and opposite action and reaction forces. And so you feel your weight. If you didn't have the chair, you would simply accelerate towards the centre of the Earth or until you hit another surface. And when you are accelerating in free fall, you feel no weight. You have, even though you are still got a weight force on you because you are being pulled down towards the centre, you do not feel your weight. So the weight that an astronaut would normally feel is because of their weight on the chair. So sitting on the platform ready for a launch, an astronaut feels their normal weight because they're strapped in, lying on their back, just like that. Suddenly, the rocket starts to accelerate forward because of the thrust. So we get two forces up. The first force is the force of the chair pushing up, that's 1 mg, plus the rocket's force T. As a result, the astronaut feels an increased force upon them, and we call this increased force G-force. Now, what is G-force? It's going to, oops, there it is. We're going to talk of G-forces in terms of G, and G is just simply a multiple of 9.8. So if I have an acceleration which is approximately 20 meters per second, just like there, then that is 2 lots of 9.8, so it's 2G. And we approximately round these things to the nearest G, or nearest half G. So 25 is about 2.5 G, and 50 is around about 5. They're all approximately 5G. Now, what is a G-force? If a person experiences 2G, they feel twice as heavy as they would normally. So if a person had, say, a mass of 100 kilograms and they were travelling at a single G, which is on the surface of the Earth, they feel as if they are 100 kilograms. That's their normal weight. If we suddenly accelerate that person at 2G, though they do not change their mass at all, they feel as if they are 200 kilograms. There is no mass change, it simply is an apparent weight change, apparent mass change. It's only because the rocket is accelerating, and that's adding to your feeling of being pressed into the chair. So if this person here would be 5G, they would be feeling as if they are half a tonne, which means that large people with 100 kilograms there would probably find it difficult to breathe or operate the machinery within the cockpit of the rocket. So, going through here now and looking at the formula for G-force. The formula for G-force is, and you'll be using this later on, G plus A over G. The division by g simply here is to give it as a multiple of g. So you add 9.8 plus the acceleration of the rocket, whatever that is, and divide it by g, and that gives you a multiple of g. So, looking at what is happening just before liftoff. Just before liftoff, there is no thrust. So the only forces on the rocket are simply the weight force. And that means that our astronaut is pulled down at the same weight force. But the seat, because this person is strapped into a seat in the top of the cockpit up here, lying on their back, they are being pushed up by that seat at a single value of mg, because it's equal and opposite, and that would mean that they have a value of plus 1g, plus being is forward pushing that way. Okay? So they feel 1g. In other words, they feel their normal weight. 1g is they're feeling their normal as if nothing is happening, because they're not accelerating. Then we turn the engines on. Now, engines have a specific design. The complication of creating engines over the last half a century is that we can't easily manipulate the amount of thrust from an engine. So we either have an engine all on or all off. And what happens is when we ignite the engine, it builds in thrust further and further up until it reaches what we call its maximum thrust. And from that moment, it remains constant. So throughout the launch, constant thrust is maintained. Then after we have this, this constant thrust, the only manipulation we have of that is we either turn it off or on. So thrust is either full on or full off. So once there is the first build-up, after that moment, we only have on and off switches. So eventually, we get thrust building up there, and when the thrust value here is the same as the weight value here, that is the moment where the rocket is hovering just above or on the launch pad. Once the thrust value, once this one here gets larger than the weight value, then the rocket starts to move upward. Now, it moves up now because if you have a look at this one here, the mg, the weight value is smaller than the arrow. So this is just prior, just at that moment of launch. So we have, let's go, that's the moment before. I was wondering where this slide was. That's the one I'm looking for, sorry. Right, just a few seconds or a few moments after liftoff. It shouldn't be a few minutes, it should be a few moments after liftoff. And we have a look here, and we see that the thrust vector is larger than the gravity vector. So we are now moving forward. Now, to work out the acceleration, now let's just give it a value. Imagine it is around about 12 meters per second squared at this moment, just for a figure. We can work out how many g that is. This would equal 12 divided by 9.8, which is approximately 1.2 g. Okay? So if it was working at if that was the value, if it was going up at 12 meters per second, then the acceleration is now at 1.2 g. In this example here, we have the acceleration of the rocket as being 0.5 g, which is equal to 4.9 meters per second squared. So we're imagining now that the acceleration here is 4.9, and we still have normal g of 9.8 being pulled down, which means the seat is pushing up at 9.8. So this is the convenience of using g. We can simply just add these together. So we've now got the seat at pushing up at 1g, and the rocket is accelerating at half a g. So the overall rocket's acceleration is now 1.5. Now, what does that mean? So imagine this person here, and we'll just give it a nice, easy value to cope with. Imagine that person is 100 kilograms. Okay? Though they don't get any more mass, they now appear to themselves as 150 kilograms. So their arms will take another half time again, so it's about 1.5 times as difficult to manipulate buttons on the dashboard of the cockpit. Their lungs are working 1.5 times as much, trying to breathe, and so is their heart. At this stage here, the blood vessels of the brain would start to find it difficult to keep the blood circulating throughout the brain, and therefore the blood would start to pool in the back of the head. This causes slight faintness. So if we keep on going, 5 minutes after launch, imagine now that the acceleration is 2 times g, which is 2 times 9.8. So the rocket is going at 19.6 meters per second squared. Okay? So this acceleration here of this thrust causes an acceleration of 19.6. So this is the rocket's acceleration, it's 2g. Don't forget, always the seat is pushing this, this astronaut up at 1g, so they overall feel as if they have a force of 3g on them. Okay. So once again, if it is a 100 kilogram astronaut, they would now feel as if they are 300 kilograms, 3 times their weight. This means that their arms would take 3 times as more effort to manipulate things, and objects would feel that if they are carrying objects, that would be 3 times as heavy. Their labouring of their breathing would be increased, and so on. There would be large masses of pool of blood in the back parts of their body. Now, this gives us a reason for why we have the astronauts lying horizontally. So if we're lying them horizontally, of course, that means that the blood pools in the back of their head, but it still maintains in their head. If they are seated vertically, so we are seated like this, the blood starts to drain down into their legs and drain away from their brain, causing them to black out or faint. So we maintain them in a horizontal or a prone position. Ever since the 1970s, when we went into the moon and into space for the first time, 60s and 70s, we have maintained that the safe level is 3g. We will not accelerate the rocket into a point where the total acceleration or g-forces on the astronaut exceed 3g. This means that the rocket must not accelerate at any more than 2g, which is 19.6 or approximately 20 meters per second squared. Now, why is this g acceleration in terms of g increasing? And to understand this, we have a look at this, this diagram here. Now, this bar here, this thing here I'm moving around now, represents the fuel tank. And on the surface of the Earth, where it's just seated here, we have a full fuel tank. And the gases are going to spew out the back at that force there, at T. If they spew out at that force there, they are going to cause the rocket to go this way at thrust. Also on the surface of the Earth, there is 1g pulling the rocket down, and the astronaut of course as well, and therefore there is 1g pointing up, and that's also pushing the astronaut up. So these two values here, these two, that one there and that, cause the acceleration felt on the astronaut. Now, when we start to accelerate, what happens is that the gas which is inside the fuel tanks gets spewed out. So this here, massive amounts of gas get spewed out the back. This causes a lowering of the fuel in the rocket. If the fuel lost, what will happen to the mass? The mass of the rocket decreases. And if we keep in mind that the acceleration of a rocket, according to our formula, was T minus mg on m, and we remember that the thrust, that's the backward thrust of those gases coming out, is kept at a constant rate because the engines are either on or off, then there is, that's unchangeable. This G remains as 9.8. What is happening is M decreases here and here. Now looking at this as a simple fraction, if we were to lower the value of the denominator of fraction, the value of the fraction would increase. In other words, the acceleration will increase. So as this mass down here decreases further and further, as we go down, then this acceleration is going to increase here. This is the maximum acceleration allowed on the rocket. So we now have the acceleration of the rocket at 19.6, which is 2g. So the acceleration is 2g up. We have a single g value on the seat pushing it up. So we have the overall value of the acceleration of the rocket as 3g. Once again, what has caused this acceleration, this increase of the acceleration is caused by this here decreasing further and further. And as it goes down further and further, we have greater increase in acceleration. When we get into orbit, we turn off the engines. When we are in orbit, we actually are in free fall, and we'll describe and examine that later on. When we put things into orbit, we actually don't want any extra fuel. If we have fuel that's not needed, it's just a waste, because most of the time when we put satellites into orbit, the rocket is just extended and burnt up on re-entry. So if we put a human into orbit, we often want some fuel there for re-entry to bring them home safely. So the question mark here is sometimes there is fuel, sometimes there isn't fuel left to manipulate our rocket. Okay? So just to very quickly summarise, we start with the vectors on the rocket, that the thrust vector is always constant. So this, and this, the three vectors here, always remain. But what does change is the weight vector. The weight of that rocket vector there is quite sizable compared to the thrust vector. But this decreases because m decreases. And as m decreases, we get smaller and smaller. And therefore the subtraction, the T minus mg, the top part of the formula, the difference becomes more marked. And once again, this thing here decreases as well. So we don't just get a decrease up here, we also get a decrease there. So, to summarise, a rocket has accelerating acceleration. Don't forget that according to Newton's second law, we have the force equaling ma. Now the force is the thrust. Now the thrust is constant. If the constant thrust, as we've got here, and we have a decreasing m, as mass decreases, then what must increase? A must increase to keep this as a constant value. Okay? So as m goes down, a increases. So this is the acceleration of the rocket. And finally, just to summarise, that for safety reasons, the G-forces on an astronaut do not exceed G throughout the launch. So that means that the craft is not allowed to exceed 2G acceleration. That's the rocket. Okay? Don't forget the plus 1G is because of the seat or the reaction of the seat. In the past, you'll find if you do some research that in the old Saturn-style rockets in the 1960s and 70s, we did get up to 6Gs, and that was, we now limit that to 3Gs. And finally, astronauts are launched horizontally to limit the effect of G-force on the human physiology, and it'll be explained that most of that is to do with blood being forced from the brain and causing them to feel lightheaded and becoming unable to operate the craft and becoming confused and so on. At very large Gs, we can even cause structural bone problems and dislocations and so on. And also breathing becomes very difficult. Okay.